Hi, I'm Curt Frye. In this movie, I want to continue my variations on the traveling salesman problem by looking at how to optimize the number of drivers if each of those drivers has a different cost per mile. The file that I'm using is tsp_diff driver costs, and you can download it using the link that I provide in the video description below. So as I mentioned, I have 4 drivers. And what I've done differently from previous movies in this playlist is to add a cost per mile. So before we'd assume they all cost the same, but in this case, driver 1 is 50 cents a mile, driver 2 is 45, driver 3 is 60, and so is driver 4. I have a second copy of the original values here in case you want to change what's in the blue cells here, and you need to remember what to change them back to. The drivers can visit stations 1 through 18, and stations 19 through 24 are actually duplicates of the start, and they start from station number 25. If I go up, you'll see in the station list over here on the left, in columns A through C, I have 19 through 25 all at the same position. And the distance matrix on the right reflects that. So I have consistent values here at the bottom, which shows the distance between each of my stations. And if I scroll down, I have the route map over on the right, which indicates the route that each driver will take. And even though you don't necessarily see Route 4, because each of those has a 0 distance, the medium blue here kind of looks like the Victoria Line indicator on the London subway map, shows that in fact there is a point there. And the values for the chart come from down here. These are all things that I've covered before, and in fact I cover the map in a movie of its own. So let's keep this visible and then go up to the Data tab of the ribbon, click Solver, and we will start our solver model. We want to minimize our total cost, which will be here in cell G48. And actually, I'll click Close so we can take a look at the formula there. G48 is a sum product formula. And what that does is multiply corresponding values from 2 arrays together. So here we have F41 to I41, which are these cells here. So we'll multiply F41 by B44, G41 by C44, continuing on, and then find the sum of all of those values. So that is what a sum product formula does. Now I'll go back to Solver, and we want to minimize the value in G48 by changing the cells in the range from B34 to E39. So those can be from 1 to 24, which means that I need to add those constraints to the solver model. So I will expand the dialog box, and I'll change the solving method from GRG nonlinear to evolutionary. And that's because our problem is definitely not linear, and it is also definitely not nonlinear. So now let's add our constraints. I'll click Add, and the first constraint will be to make sure that all of the values from B34 to E39 are less than or equal to 24. Click Add. Same cells are greater than or equal to 1. Click Add. And also that they are all different. And that's because we only want each station to be visited once. So the same cells, B34 to E39, and then the comparison operator will be diff. So they are all different, and click OK. Finally, I want to make sure that I have boundaries set for the top and bottom values that will be used for the difference range. So I am set to evolutionary. I'll click Options, go to the evolutionary tab of the dialog box, and require bounds on variables is checked, and that is something that we need. Click OK. We have 1 through 24 as our bounds. They must all be different. I'll click Solve and come back when Solver has found a solution. And we're back. It looks like we have a 4-driver solution. I'll click OK and take a look at the map. So this looks like a pretty good solution, actually. We have all of our curves with no crossings, and it also appears that we have allowed every driver to stay at the start or go back home early to save on distance. So here we have driver number 1 starting at 25 and going to 23, which again is a copy of 25, and then driving out to these 5 stops. For driver number 2, they do 5 and then come back to 21, which is again a 0 distance. Then driver 3 goes 24 and 19. Those are also at the origin point, same as 25. And then for driver number 4, they start at 25, 22, and 20 as their 2 first stops, even though they don't actually move. And then we get the distances below. But what's important is that the cost is very low, $166.85. And that is because we are able to optimize based on the cost per mile for our drivers. Now let's try it again with a different set of values. So let's say that I set driver number 2 to 75 cents, so 0.75, and driver number 3 to 50 cents, 0.5. There we go. And with that in place, I can reset my values here. I'll just type a 1 and select all the yellow cells so that they all go back to a value, so I do not have a valid solution. Then go up to Solver and run it again. Solver has found another solution. I'll click OK. And this is a 3-driver solution, but it honestly doesn't look like it's optimal. So I have driver 2 being left out, and that's interesting because that driver, oh no, it actually has the highest cost. I was looking at the original values. So driver number 2, because it has the highest cost, has been left out. But if we look at the paths, I can see that there are multiple crossings. So we have a crossing here, and we have one crossing here, and those are the only 2. So I'm going to keep this solution and rerun it to see if we get a better outcome. So Solver and solve, and we'll try again. All right, we have found a solution. I'll click OK. And here, even though driver number 2 has a very high cost or relatively high cost per mile, they are still included in the solution, but only for 2 stops. If you look here for the distances, we have distances of 0 for 4 of his stops. So it appears they will drive out to 11, then to 10, but back to 19, which is, again, is a duplicate of the starting point. So they only actually visit 2 stations. However, the other routes look pretty good. We don't have any crossovers, and the total cost is slightly lower. So instead of $173.30, we have $171.45. So that is a very interesting look at a traveling salesman problem where each driver costs a different amount of money per mile. And it also demonstrates that you might have to rerun your model to try to get it off of a local optimum, such as a local maximum or local minimum, to see if you can find a better solution. And visualizing that solution makes it easier to realize when you should do that. I hope you enjoyed this movie. If you did, please like it and subscribe to my channel.